paying attention to the feedback. So, we're going to talk about potential this morning, hopefully wrap up. And then Thursday we're going to turn our attention to the concept of capacitance. So let me just remind you where we got to Thursday last week. We defined the idea of electric potential, in particular a sort of relative change, very much connected to the definition of electric potential energy. So remember, this is an energy originating concept. But what we do is pull out the effect of what might be called a test charge, Q0, so that we're not kind of explicitly dependent on that, and that allows us to define the potential. Okay? We also learned on Thursday a useful relationship that we can determine changes in potential by doing a path integral as we traverse some trajectory in an electric field. And in fact, I think I'm going to move relatively quickly on this rather than formally derive this in class. You already told me the answer last week. If you'd like, you can look at some notes of mine when I post them after class, or just take a look in our textbook. But of course, the inverse relationship for that way of calculating change in potential, if we're given the electric field, is simply arrived at by differentiating the potential. And let me just talk you through this a little bit. Remember, vector quantities. We arrive at something which is a scalar, which is a large part of the value of defining this thing, electric potential, as we're about to see. And so if we're going the other direction, I've got a scalar, but I want to reconstruct something that's a vector quantity. Of course, what that means is, well, for our purposes right now, some of you know vector calculus, but for our purposes right now, if I want to figure out the electric field along some particular direction S, I'm going to take this scalar quantity and differentiate it with respect to that particular coordinate, and that will give me the component of the electric field in that direction. Okay? So again, some of you know vector calculus, it's kind of one coordinate of a potentially three-dimensional derivative. And of course we can build this up with the three coordinates and reconstruct the electric field. Okay? So that's roughly where we got to last time. So I want to explore potential a bit more today, do a few examples, and we're going to start off looking simply at the expression for electric potential associated with a point charge, about as simple as we can get. We'll throw in our definition of the absolute potential being zero at infinite distance. We'll get a relation for the absolute potential. And then I'm going to do a couple of worked examples, one of them on a discrete superposition and one of them on a continuous sum. And then we'll sort of move things along. So, with that in mind, let's talk about now the potential. This is going to be absolute in a moment, associated with a point charge. And we're going to figure it out simply by making use of this definition of how we can calculate the change in potential. So I'm just going to take a point charge, let me call it plus Q. And as you know, the electric field is radiating radially outwards. And I'm going to look at a point, let's say P, the distance big R away. And I'm simply going to move this, I'm going to take a test charge Q0. So I'm going to put this at some random position indicating that I'm moving it. Test charge Q0. I'm going to move it a small amount dr. Eventually I'm going to move it all the way out to infinity. Okay? So very simple. Point charge, it's got an electric field associated with it, it's got an electric potential associated with it, which is what we're about to calculate. I'm going to start off with my test charge. I'm going to move it along a trajectory from some initial point at distance big R, and I'm going to take it to infinity. I'm going to calculate the line integral set by zero at infinite separation and see what expression I get for potential. So it's really quite straightforward. So I'm moving this from here to infinity. So test charge from R equals big R to So I'm simply going to take my expression now for the change in potential. There it is, slightly re-expressed now. I know the electric field associated with a point charge is a function of radial distance r. We know what that is. I'm going to throw it in a moment. And I'm taking a path, path element dr. Now, as we know, since this is a conservative force, energies, potentials don't depend on trajectory, I can choose a path here that makes my calculations simple. Of course, I can choose any path between 2 points, and the answer is the same, but it's always advisable to choose a smart path that simplifies the calculation. So no big surprise, I'm going to take just a straight line radial trajectory out. And that means, if you think about this, my electric field and dr are always parallel. So my scalar product gives me unity. So again, simplified, the answer is universal. So what does it tell me? It tells me, and here's where I'm putting in my value for the absolute potential of infinity. It's going to infinity. That's my final point. I'm going to set the potential to be 0 at that point. So 0 minus the potential at point P is now simply the integral from big R to infinity of E dr. You know what this is. Go up here so you guys can all see it. And so this now tells me that minus Vp, which is this thing, is minus the infinity from the integral from big R to this of kq over r squared dr. Okay, so it couldn't be simpler. Here's my expression for the electric field as a function of radius. We learned that a couple of weeks back now. The scalar product has disappeared because it's always unity along the path that I've chosen. And so what this tells me is simply that the potential at point P is just a cubed over r. Okay? So it couldn't be simpler. So that's how we get an expression for the absolute potential at a radial distance big R away from a point. Of course, in general, that's a variable, so I'm going to throw it back and make it a little r as a variable. And again, the only thing I've done here along the way was set the potential at infinite separation from 0. Fine. So now we've got this simple expression for the potential as a function of distance. Remember, it's a scalar. There's no vector information anywhere here. And remember, it has a sign. And it's on this. If it's a positive charge, it has a positive potential. If it's a negative charge, it's a negative potential. So since we're often going to be representing things visually, let me write this as V as a function of R, and a function of R for a positive and then a negative charge has a 1 over R dependence like this, 1 over R dependence but with a negative sign. Okay, so it couldn't be really any more straightforward than that. Okay, so now we've got it for a point charge. As always, that's the basis for us to start building up more complicated charge distributions. So a simple way of getting you to think about the virtue or the value of having this be a scalar quantity is the problem on the left. And rather straightforward. Okay, take a look at the one on the upper left. I'm going to give you 2 minutes to talk about this with a neighbor. Let me make sure you can understand what's happening there. A little bit of that shadow right at the top. So upper left diagram. There are 6 point charges arranged around a rectangle. Each of those lengths between 2 neighboring charges, if you go around those dashed lines, each of those lengths is the same, has a numerical value. I'm not so interested in as usual, but if you want, you can do the numerical part. And then the charges are distinguished by multiples of Q1 and Q2. Okay? So, the question is, what is the electric potential at the center of that rectangle? Okay? So, talk to a neighbor quickly. Remember things I want you to think about. The fact that the electric potential is a scalar, not a vector. And think about symmetry. Noah?
Is the length of the longer side 2a?
Yes. Okay, so I'm going to give you 2 minutes, talk to a neighbor, and tell me what the answer is. And do talk to a neighbor.
Because it's scalar, you just add them. Yeah, you don't have to worry about vectors. So you just calculate the voltage that point feels from all the charges and then add them all together. And you can figure out all the distances using like
Yeah, it would, but you could just add it. Like so you add up all the voltages for each one using the distance, so that is important. So in that sense, like direction is important. But after that, you can.
But we still need to get the R.
Yeah, but you have to like do like
It's
your
just
A
trigonometry.
squared.
Yes. So then you just get that one and you add them all up and it's cool.
So I think it's
yeah, isn't there a blue X with like stars?
I forgot it.
you haven't seen it.
Isn't there a blue X with like stars on it? And
I feel like it's red.
Well, it's red.
Because I looked at it.
I think you're thinking of their battle farm.
They have two phones.
Yes.
Oh my god.
And everyone else.
Okay, some of you are not being friendly enough.
I see.
Okay? I want you to be more friendly. Okay, 30 seconds. This is not difficult, but I just want you to tell me a quick way to get to the answer. So 30 seconds, and if you're not talking to a friend, please do.
That's good. That's good. That's good. A squared plus 2a squared.
No, but I know. I see.
Okay, time's up. What's your approach?
Would you just do KQ over R for each one from the center of that, so you would just do a bunch of Pythagorean stuff to get the quarters? That's it. And you add them all up. So actually,
Okay, so of course, these are all point charges, so we're not going to worry about integration. It's a direct summation. So of course that approach is going to work. Yes, Pythagoras or whatever, but is there a way to lessen your workload? Let's get some new volunteers. Yes, sir. Good. So I'm going to repeat that so everyone can hear it. The four corner charges add up to 0 in terms of their contribution to the potential at the center. So first off, they're equidistant, right? Just by symmetry of the rectangle, they are equal distances away. Now, if we were dealing with electric fields, life might be a little more complicated because we would have to worry about directions. So if I look at the lower right and upper left corners, there, even if I was dealing with a vector quantity, namely electric field, I'd have cancellation. Equal charges, equal. But in terms of the lower left and the upper right, in terms of electric field, I wouldn't get cancellation. I'd end up with something I have to worry about, because they're different charges but at equal distance. But I'm dealing with a scalar quantity, so all I care about is magnitude and sign. And so in this case, since everything on the corners is equidistant, all I do is add up all the positives, add up all the negatives, and of course I get exact cancellation. So those four corner charges contribute nothing overall to the potential. Okay, so that's the key point of this problem. So what's left are the two charges along the midway of the sides. They certainly don't cancel, they're equidistant, but they're equal charge as well. So in this case, I would simply have from the upper one and the lower one, so I have K for one of them, K Q over R. What is R? It's K over 2, right? It's half a length distance away. And I would have this times 2. So this would give me positive, that's what I would get for the absolute potential at the center of this rectangle. So for those of you who like numerical answers to feel comfortable, it turns out that this is 2.2 volts. But as usual, that's less important than the mechanism to get towards the answer. Okay, so repeat how I get the four corners cancelled. So remember now, the value of working with electric potential is it's a scalar. I don't care about direction, which is, as we're about to see also in a moment, particularly helpful. So all I need to do is worry about Q's and R's. Those are the two variables that come into each contribution of potential. And those four corners, obviously, by geometry symmetry, they're the same distance away. And so all I care about is actually summing up the total magnitude of the charge, right? So I've got +4 from the upper left, lower right, and I've got -4 from the lower left, upper right. And so in terms of charge contributions, that cancels and we get 0. Now again, if I were working with electric field, life would be a little bit more complicated. I wouldn't have direct cancellation in that case. I don't look enlightened.
I was just thinking of it like differently. Now that you said it.
Yeah. Okay. Other questions? All right, so let's move on to one that shows this in a bit more of a compelling way, which is the one in the middle. So it's a familiar problem with a little bit of a variant now. And so now we've got a continuous charge distribution running along the length of that rod, which is aligned along the x-axis. And I'm going to claim I have a local charge density, linear charge density lambda, just dq by dx, which is constant. And in this case, I want to find out what is the potential at that point in red, which is perpendicular to one end of the finite length rod. Now, if this was an electric field calculation, what would you do? It's not, of course, it's an electric potential calculation. If it were an electric field calculation, what would you be doing?
Pick like a differential element from the rod and then calculate its charge based on like the linear density and then calculate the distance.
Yep. Okay.
And then integrate it.
Okay. All good. So I look at a point. I've labeled a little length element dx here. It has an associated little charge element dq. I can do my usual E equals kq over r squared calculation and figure out what the contribution to the electric field at that point P is. And then I have to integrate. So everything up to the integration is standard. You've seen it before. The integration here, however, suffers from something which is not pleasant. Namely, what is it?
You don't have the symmetry we're
I
used
don't have
to.
the symmetry anymore. So in past cases, we've looked at scenarios. The analogous thing here would be I'm at the midpoint, or it's an infinitely long line, in which case I could claim I'm always at the midpoint. But I'm not at the midpoint now, so I don't have cancellation of electric field contributions in the direction that's parallel to the line of charge. And so I have this nasty, not only do I have to sum up the magnitudes of the electric field components, but they come in with varying angular contributions. So that's not pleasant to work with. Of course it can be done, but it's not pleasant. But now I'm going to calculate this in terms of electric potential. So it's a scalar. I don't care about directionality anymore. I just care about magnitude. And so that makes my life an awful lot easier. And so just to kind of remind you how this will go, I'm going to take this point here, and I'm going to say that the contribution to the electric potential at this point is just K dq over whatever my R is. So this now is K lambda dx, the usual substitution. And in terms of the parameters I'm given, this looks like I've had in the past. So I'm casting this now in terms of x as the variable that I'm going to integrate over. It's the hypotenuse of that triangle, now cast in terms of x, distance d away. So now I have to integrate, as usual, but again into scalar. So my life is a lot easier. So this is just now the integral. I'm pulling lambda out because I've claimed it's constant. And so what I'm left with is integrating from x to big L, this, and this would be an example of an integral I'd give you the answer for on a test. So this turned out to be, well, I don't want to do all of this, maybe not so interesting, but k lambda, what is the result of that integral? It's the logarithm of x plus root of x squared plus t squared, and again, evaluated between my limits here. It turns out, if I simplify this a little bit, that it is the following. So, nothing really new in here in terms of approach, but we've forgotten, or we've been able to forget the directional dependence, so we've got a calculation that we can at least work with. And that happens to give us the result. Any questions on that? Now, you might ask, well, is there any virtue in just calculating the electric potential in and of itself? Maybe yes, maybe no. But remember, some of our introductory comments here, that I can, in principle, if I know an expression for potential as a function of three-dimensional space, I can determine or derive the electric field simply by differentiating that. So this now gives me maybe a mechanism to get to electric field results in cases where the geometry and the symmetry associated with it don't make my life so easy. All right, so, yeah.
So, sorry to go back to the first example. It's really not sitting. There's minus 3q1 on the top right, and then minus q1 on the bottom left. Wouldn't that charge imbalance? Like, there's no cancellation there. There's cancellation with the two positive 4q2s. So I really couldn't get why you're doing 2 times k 4q2 over a over 2 when you got some sort of charge imbalance here, but like charge cancellation here.
So this part at the bottom here simply is associated with the two charges along the middle, along the sides of the middle. So what I've done prior to this is claim that I can ignore everything on the corners. So to come back to your question, how do I get cancellation? So we know from here the potential just depends on the charge over the distance. And so all I need to worry about here is, and again, the distances are all the same for those 4 charges in the corner. So in that sense, I could bring this out and just have k over r, and then I'm worrying about the sum of each charge term. So in a sense, this is why this problem is chosen, obviously. You kind of, well, I'm not quite sure how you look at this, but when you look at the upper left and the lower right ones, in terms of electric field, you imagine there's cancellation, but there's not cancellation for electric potential. Okay? Equal sign, equal distance, so they both contribute to a positive electric potential. Okay? And then when you look at the lower left and upper right, you see it's not symmetrical anymore. So not only do you have contributions now in terms of contributions, negative contribution to the potential, and again, they're the same distance away, so all I care about is adding up the total values. But in this case, what you would expect is their contribution to the electric field at the center doesn't cancel, whereas in the first two it did. In this case, it doesn't. So it's not a completely straightforward relationship between E and V, but it's straightforward in this sense, and you could kind of play around with that if you wish. But the important thing is to look only at magnitude and sign, and you don't look remotely convinced. No? Elizabeth.
So it's not the fact that the plus 2 and plus 2 can't speak. Plus 2 and plus 2 cancel. That's not the point
That's not the point.
The
It's
net-
the for.
the net
It's the
constant.
cancellation of the for. That's the point. Though it's interesting to look at, because I want you to think also about electric field here. In terms of contribution to the electric field, the +2 do cancel in terms of their effective descent. But the other pair do not. Okay? But indeed, it's the overall summation in this case that's important. Yeah.
Well, what is the base you're adding the like you're basically adding the diagonal lines.
So why am I adding the diagonals? Simply because I want to look at things that are equidistant, right? So we know that potentials from point charges go as 1 over r. So if I can look at sort of fixed radial distance away, I have an equipotential there. And so for the points on the 4 corners, the point in the center, which is where I'm trying to calculate this thing, is of course the same distance away from all of those 4. So when I look at that, I go, okay, maybe that simplifies my calculation, and of course it does. And then when I'm left looking at the remaining 2 that are closer in, again, they're equal distance away. So all I need to do there, it's kind of like taking out the r term here as a common constant for certain subsets of the charges, and then only worrying about the total charge, because that helps me do the cancellation more. So this was chosen for good reason, because it's sort of simple, but conceptually makes you think a little bit. All right, good. This result, I'm going to be brief on this and ask you to look at my notes and also the textbook. So this is the potential a distance d away from a finite length of charge, where the length is given by big L. What does that expression become if L is infinite? D is finite. So this one. L becomes infinite, D is finite. A little louder? Yeah, diverges to infinity. Not a pleasant thing in physics, though it happens more often than we let on in intro physics. Yes, it diverges, becomes infinity. So for an infinite line of charge, since this result does give us an infinite potential, what we are often led to do is actually simply go back to using a difference in the electric potentials between 2 radial distances away. And you'll see what maybe I mean about that in a third example in just a moment. Which is to say, we're going to pin, or we're going to define a